Let's check if this is recording. Okay. Hey guys, David here. Today we'll be doing problem 2, Year of the Cow. Yeah, so this was from the February contest. I would say this is the easiest problem of the bunch. I think Just Green Enough was actually really hard. I had a lot of time struggling on this, and like the editorial is not so great. It's okay. I would say it's not so hot, but Year of the Cow is pretty smooth sailing. It's just a greedy algorithm. So the idea is, imagine like a number line, right? And Bessie is on the present day, which is 0, and she has a time travel machine. And so what she can do is she can move like back and forth in time in intervals of 12. So she can only time travel on years that are divisible by 12, like 12 and like, I don't know, 144. And she can only land on years that are multiples of 12 as well. And so her goal is to meet all her ancestors. So these are all her ancestors. And so in this case, it would be like 46, I think 85 and 95 was one, 100 and 101. Let me just check that real quick. Yeah. And so her goal is to meet them. And how do you meet them? So what you can do is when you time travel, let's say to like 46, because that's a multiple of 12, she can wait 2 years and she can meet him. Now remember, Bessie can only time travel, or she can only move this way in time, because that's how time works. It only moves in one direction. She can't like here, 84, that's a multiple 12. She can't wait 1 year and like go back in time and meet this guy right here. Yeah, so I'm gonna mark all the important dates, or actually all the important intervals that are multiples of 12 that she may want to time travel to real quick, and it'll be easier to explain later on. Yeah, I'm gonna wait. So yeah, so basically she wants to meet all these people, and she also wants to minimize the cost of waiting. So the cost of waiting here would be 2, the cost of waiting here would be 1, and 7, and 8, and so on, and so on, and so on, and so on, and so on. Now here's the deal. Because she can only time travel, and she has to land back to 0, by the way, at the very end. Because she can only time travel on intervals of 12, what happens instead of 2 years, it's going to be 12 years, because she has to get back to her destination on 12. So it's going to be 12 years actually. And you'll notice that these guys are connected, and that'll be important later on. And so yeah, and then at an interval of 12, in order to save time, you can just skip back to 0, which would save a lot of time. Yeah, so you want to minimize the cost. The cost would be her waiting. Now, another catch would be K. So K is the maximum amount of times she can time travel. And so I guess, like, let's say you want to time travel to 108, that costs 1. That costs 1. Maybe you want to time travel to 84, that also costs 1. Time travel 36 if you want, that also costs 1. And you can only do it K amount of times. Actually, wait. I'm gonna keep this over here. I never use the lasso. Like, what the hell? Can I like select all of you? Please. Okay, let's. Bro, just let me select all of you so I can move you. Copy maybe, delete, paste. What the hell? Anyways, whatever. Y'all know what K is. So yeah, she can only time travel up to K times. That's the basic idea. Now, let's just go through the example. They give you 5 and 3. So 5 is just the number of ancestors that they have to meet, and 3 is obviously k. So we'll mark it in white. How about that? So first things first, you kind of want to go to the very back person first, or the person furthest from 0, because that way you can time travel this way and you don't have to bother like this example. Like, let's say you were on year 84 and you wanted to meet 85, you would have to jump back and wait 12 more years. That's just a hassle. So you want to start at the back so you don't have to bother with like people that are in the past, more in the past. And so so the first cost would be going here, time traveling all the way back over there. And so that's 1. We'll mark k over here, so 1. Then so the optimal path is you wait 24 years, right? You wait 24 years, then you time travel here, wait 12 years, and then time travel here. That's 3 times. So that looks like an R. Wow, that actually does look like an R. There we go. So yeah, that way the minimum would be 36. That's how they got 36 here. So what to do? So how about this? Let's just change up the question real quick. What about 1? That's a very easy example. What if you can only time travel once, right? Actually, yeah. What if you can only time travel once? What can I do? Well, the only answer is I have to wait 108 years from the back and get to 0, because there is no other way to reach every single ancestor without time traveling. So you have to wait 108 years. Now, let's raise the question, what about k equals to 2? Well, I can still wait 24 years, but then I have the choice to either time travel here and wait a total of 12 plus 36. 36 is here. This little gap right here is 36. I can wait 48 more years, or I could wait and skip this, also 48 more years. So technically, both these are optimal. So in total, that would be 72 years. So, okay, if you haven't noticed the pattern, kind of the greedy approach is to like find these segments, right? Okay, right now there's 2 segments, 1 and 2. Notice how these are connected, right? There's 2 main segments. And so that means it would require number of segments plus 1, because plus 1 times to get optimal. Okay. Right? The number of segments plus 1 time. Actually, let's just reroute and like imagine there's no such thing as like k, right? There's no barrier. The optimal path would be the number of these groups. So in this case, there would be 3 groups because 85 and 95 are between the same 2 multiples. 100 and 101 are between these 2 multiples. 46 is between these 2. So 85 and 95 are in the same group, 101 and 100 are in the same group, and 46 is in its own group. So optimally, it's the number of groups times 12. So if we had an infinite number k, the optimal amount is number of groups times 12, right? Now, if we had less k, right, we would have to count the gaps between groups. So the gap here will be 36, and we would also have to count this one from 0 to the first multiple of 12. That's important, and because there's also the choice of weighting here too. And let's see, and the gap between here is actually 0. So what we can do is finally at the end is, so yeah, that'll be important later too. If this is the kind of answer. If the number of groups plus 1, 2, 3, wait, 1, 2, 3, and then 4, yeah, plus 1 is less than or equal to k, that means it's the optimal. So that means it's number of groups times 12, because you only need the number of groups plus 1 times in order to get the optimal path. And the reason why there's plus 1 is because there's the initial arrow going back here. So optimally, you would go here, go to the next group here, go to the next group, or yeah. So optimally, you go here, go to the next group. In this case, there's not really a gap between, like 36. Pass through time, go to your next group, saving 36 years, end your group, and then go to 0 at the back. So that would be 1, 2, 3, and then 4 for this one. That's kind of how it works. So yeah, if that's true, the number of groups is just the number of groups times 12. Else, so what we do is we get these gaps, right? And let's just put them into an array, and we'll also sort it as well, right? Else, we would just find the difference between this. We would loop through this array, and for every index that's between number of groups, I think it would be -1, if I'm sure, if I'm correct. Yes, oh, +1, +1, +1. Yeah, and you would just add the minimum amount. And the reason why it's sorted is because you always get the lowest possible gap, so you can save more time. Yeah. So wait. Yeah, you loop through these, and you just add to the following, or you just add the value to your answer to this actually. So it's just the number of groups times 12 plus, let's just say array A, 1 through k minus groups plus 1. So it's a little hard to understand, but this is a very common problem. If you want to like reduce the cost of like these segments, you just make an array of distances or gaps, and then you sort it, and then you take out the minimum every time. So you just save more to your cost. So we'll look at the code real quick. So kind of how it goes is I take input here. So this is just input, right? This is also input as a vector, so I just literally take it n numbers and put it into a vector, which is a dynamic array for whatever language you use. I have a set, so like in Java, tree set, and so I insert, or I just put in like these numbers, right? And so these numbers are the actually red numbers, so they're the multiples of 12 that are important. And you'll notice that there's two important numbers, right? 46 and 36, or 48 and 36, right? So let's just take an example of 46. The two numbers, the highest multiple that is above it, or the lowest multiple that is greater than 46 is 48, and the highest multiple that's less than 46 is 36. And you'll notice that's just 46 divided by 12 floor for 36, and 46 divided by 12 ceiling. Ceiling is just rounding up, and floor is just rounding down. That's it. And so I just take the ceiling of the multiple of 12 that's required. So if VI would be 46, this would return 48. I'm just multiply 12, and this is just long. Then I make another vector of D. This is previous, and so what I do is I'd find this is just a way to find gaps. This is a little kind of messy, but it just helps because, so X would be the ceiling, or the highest multiple, or the lowest multiple that's greater than the value, and then the previous. So previous is the previous ceiling. And so x minus 12 would be the actual lowest, would be 36, because 48 minus 36. So x minus 12 would be the floor, basically. And so I just find the difference between the floor and then the previous, the previous one. And also, because it's in a set, it's also sorted, which is really nice. I don't have to worry about that stuff. But yeah, so you'll always get the correct gap. And so D is just the array of gaps. I sort D, and then I loop through the required amount of times to basically like minimize spans. And then I just output. That's basically it. This one was not too bad. Let's see how long it takes for me to explain. Okay, 17 minutes. It's a little lengthy, but this is really not so bad. I think the real hard one is just green enough, and I would definitely have trouble with just green enough in a actual contest. But just for the fun of it, I'll output it, or I'll just submit it to the grader. But yeah, I would say here the cow is not too bad. It's very similar to modulo. If you know what that is, it's kind of remainder. It kind of reminded me of the cycle of how that works, but yeah, not too bad. So yeah, and yeah, this is a good solution. So thank you for watching, and I hope you have a great day.